Welcome to CC Bootcamp webinar. This is Larry Metzger, and today we'll be going through the QoS for converged networks. Again, this is a presentation for convergence. We're looking at really the requirements for the Cisco CCIE converged network, but we will also bring in some best practices, real-world stuff that will help you as well in your endeavors throughout your career. So the agenda for today is QoS Overview. Then we'll go into the WAN requirements. We'll also talk about LAN requirements, configurations, best practices, and a demonstration of how all of this really works. So you'll be able to see how this affects your network and how you can actually utilize the QoS properly, not just using an auto QoS or a system QoS provided. You'll understand better how to utilize QoS within your network to guarantee that that voice application is given priority. So let's get started. So what is QoS? This is just an overview of what QoS is. In the QoS world, we have the ability to change what information goes in what order on the network. And in order to do that, in order to process higher priority information, we first have to identify the information. So we have to somehow identify which packets are more important in our network than other packets. And then once we've identified a packet, we then want to put it into a class. So we're going to classify it and then put it into this grouping, and then we will actually apply the policies to it. So over on the right, you'll see this is the description of it. So we've got packets coming in, data, voice, and we're going to sort them out into voice information, data information, and then just standard basic data. So you have your mission critical and then just everything else. Then what we're going to do is we're actually going to provide the amount of bandwidth we want for each one of these classes to be able to utilize. That way we prioritize our traffic and guarantee a quality of service throughout our network. So there's three different models that we can use for doing quality of service. Best effort model, and the best effort model is the one that your network runs under normal operations. There is no QoS. This is basically when the packet comes in, we pass it along, we do nothing to the packets. The next option is to use IntServ. IntServ really utilizes more or less an RSVP. We're going to set up throughout the network and guarantee that this packet has a specific level of quality from one end to the other all the way through the network. So it's a special QoS that requires some configuration, and it must be configured from end to end. So it just happens throughout the entire network. And then DiffServ, and DiffServ is another technique that does give us a quality of service, but it's done on a per hop basis. So each one of the devices has to be configured for DiffServ, and each one of the devices can handle each packet differently. So as a packet goes through the network, we don't have any absolute guarantee of quality from end to end. Each hop will determine what happens to that packet. So each of these options, best effort, IntServ, and DiffServ, provide a different level of performance for us, as well as a different level of effort in configuring the network. So each one is slightly different in how they function, as well as what they give us. So let's talk about the best effort model, and what does the best effort model really look like? Well, the best effort model is kind of like when you go down to the U.S. Postal Service and you say, here's my letter, I want to mail this out. So when we say we want to mail it out, we're going to just send this packet out and hope for the best. We have no guarantees. It's just a regular U.S. Postal Service letter on the network. It's the default mode for all traffic. So within the network, if you don't configure QoS, this is how your network is going to transfer packets. As the packet comes in, it's going to be passed along, and there is no special treatment of it. There's no difference between types of traffic. So whether it's voice traffic, data traffic, TFTP traffic, whatever type of traffic your network has, there's no differentiation. A packet is just a packet. So what are the benefits and drawbacks of best effort? Well, the benefits, it's highly scalable. It will allow your network to perform as well as your network can perform up to the full bandwidth that you have on the network. Very scalable. No special mechanisms required, meaning you don't have to configure anything. just turn your network on, let it run the way you always have. There's nothing required as far as a configuration. The network will run in a best effort model by default. The drawbacks, we have no guarantees. So a voice packet is likely to get dropped because there is no guarantee that that voice packet will be treated differently than any other packet. Additionally, there's no service differentiation, meaning a data packet, a voice packet, whatever type of packet, there's no differentiation between them, so therefore we can't tell what actually is being transmitted through our network, and each packet has just as much likelihood of being dropped or passed as any other packet. Now in the IntServ model, is a little different in the fact that it utilizes sort of an end-to-end guarantee. So it's kind of like in this situation we're talking about you're going to rent a jet, or you own a jet, you lease a jet. It's yours. So you are guaranteeing that you have a plane to fly you from point A to point Z, and you will definitely get there. It's a guarantee. So some applications use special bandwidth delay requirements. So this would be obviously our voice packets would definitely fit into this. And you can use this in a Cisco Unified Communications solution. In your call managers, you can configure to use an RSVP or IntServ solution. It guarantees, it's predictable. We know exactly what's going to happen because before we start sending packets, we actually send out a request to every device along the path to set up this bandwidth reservation. So we are going to reserve bandwidth across the network. So it's a reservation on our network. We guarantee the delivery. No other traffic can use that reserved bandwidth. Once I've set up this IntServ reservation from point A to point Z, that bandwidth is guaranteed and no other application can use that bandwidth. So if I've set it up for, say, a G729 voice call, which is 28 kilobits, that 28K is actually set aside for that phone call, and no other device can use that 28K because I've reserved that for this voice call. Even if there's no voice packet being sent at that particular moment, I am withholding that bandwidth and no one else can use it. So again, it's like having your own private plane. You're going to put your information on that private plane and you're going to send it, and we know it's going to get to the other side because it's our plane. So let's look a little deeper into this. What does it look like? Again, as I mentioned before, we're basically going to set up a path through the network that's going to allow us to get from point A to point Z through the network. So whether that's a phone talking across or a device that has a reservation, we've reserved this bandwidth for these devices. So as they communicate, we're guaranteed that their communication will get from one end to the other because we've reserved it. So we've used this request. Let me just put my arrow there. Request for our data. We've made the request in the network to reserve that data bandwidth. Then we have done the reservation. As we send our information through, the devices on the network will use an intelligent queuing mechanism that allows them to guarantee our packets that are part of our stream are prioritized and given the bandwidth that we've requested. So in the big picture, it does require some configurations, and it does require applications that recognize this. This has got some drawbacks to this as well, because not every application out there is going to recognize an RSVP configuration. So you may have to do some things there if you want to use this. Or if you're using, just a Cisco communications manager setup, obviously you can set up your voice traffic to do that. So again, looking a little more at what does this look like in the network. As RSVP is communicated through the network, we're basically going to go out and say, hey, I need this type of bandwidth and this type of delay. So 20 kbps and 200 milliseconds delay. Each device along the path has to set aside this capability. If any device in this path is unable to satisfy this, then IntServ will not set up a reservation, and your call potentially fails. So if you do have a need for this, you've got to make sure that the network is designed to handle the call volume or the configuration requirements that you're putting on it. Because if it's incapable of it, or if you've tried to oversubscribe, you will end up with failures because the system will not send a call out if it cannot get the guarantee. So it does have a couple of requirements within the overall design aspect of setting these things up. So again, let's look at what are the benefits and drawbacks of using an IntServ model. Well, the benefits, basically we've got a guarantee here because we have set up end-to-end a resource admission control. So we are guaranteed that this call will get through with the quality of service that we want. Per request policy admission control. So every time a call or a device attempts to set up a requirement or a reservation on the network, it's going to, each one that's requested is going to look and see, do I have resources available to set that up? Signaling and dynamic port numbers. So we can have different types of signaling. It doesn't have to be that we set up an access control list. This would be handled by the RSVP mechanisms. What are the drawbacks? Continuous signaling. In order to maintain the stateful architecture, they have to communicate regularly and let the other devices on that link know, hey, we still have this call that needs the reservation. It's a flow-based approach, so it's not real scalable. In large implementations, this gets really difficult to configure, and it's a more or less a difficult opportunity within your network. Can it be done? Absolutely. Does it create other headaches and these drawbacks of basically the reservation guarantees bandwidth to this application, but then if that application isn't using it at the moment, it's unavailable to other devices. And then it's flow-based. So there are some drawbacks here with this type of a model. So let's look at the DiffServ model. The DiffServ model is the one that we typically use in our networks. This is the solution that is really overall the best solution for a standard converged network. Not to say that you couldn't use an IntServ solution, but the DiffServ is the more common and definitely in many ways better solution. So we identify the network traffic. So we basically call it out, whether it's real-time protocol or we want to call it about ports and use an access control list. We're going to actually classify it by some means. The policy is enforced differentiated treatment of traffic classes. What does this mean? We're going to say put things into different buckets and then deal with those buckets in separate ways. So we can identify packets that are, say, real-time protocol voice packets. We can do control packets such as H323 or Skinny. We can do mission-critical data packets. We can do web packets. Any type of packet that you can identify and separate can be classified and treated differently on the network. The administrator can choose the level of service. So instead of having the application set up a reservation, the administrator is the one that actually controls this, because the administrator gets to say, I want this bucket to have 200K of bandwidth available. It's like using a package delivery service. So it's like going down to UPS or FedEx or any of the shippers, where you're not going in there and having to purchase or lease a jet yourself. You're going into a company that does this all the time, and they will guarantee you next day air, or this package needs ground service, this package needs to be delivered in 2 days, giving you different levels of service. You're not having to lease the jet, but you are able to choose what level of service for each one. So your voice traffic could be that overnight AM delivery type thing. So what are the benefits of the DiffServ? Highly scalable. You can configure the information on your network. The nice thing about the configuration is obviously we can do copy and paste, and I'll be showing you an example later on of the configurations and how you can easily copy and paste and reuse this. So it's very scalable in your network. It's very scalable because you can also set aside different bandwidth based on your links. Many levels of quality possible. It does give you the ability to really define different types of traffic on your network and guarantee bandwidth for the different types. What are the drawbacks? Well, really it's not too big of a drawback, but there's no absolute service guarantee because we're not setting up a reservation end-to-end. We can't absolutely guarantee that this is going to get through. We can guarantee on a per hop basis that the traffic will be prioritized, but that does not give us the absolute guarantee that it's going to get from point A to point Z. It is a complex mechanism. It does require some configurations. Again, it's not as simple as you have with best effort, where it's just it does its job. It does require you to do some configurations, and it does require some mechanisms by which it classifies and then prioritizes. So the DiffServ model is, again, since this is the model that we typically use out on the systems, this is the one that we'll spend the most of our time talking about. So in the DiffServ model, we've got these services that we need to associate with traffic classes. So let me just see if I can get my highlighter here. So we want to associate traffic classes. It does use complex traffic classification, and typically we do it on a per packet, and it's DSCP based. We'll go through what DSCP means and all of how you configure it and choose which DSCP you should use. It's not a per flow state. It is really not guaranteed end-to-end, so it's this per hop based behavior where you are configuring this on each one of the routers or each one of the devices within your network. So the overall goal is that it is scalable. So that's where we're heading with this whole process, is that this is much more scalable than the IntServ model and much easier to really maintain long run. So DSCP encoding, this is how we identify the traffic, and typically what you want to do is, as a packet comes into your network, you want to identify it and classify it. Once you've classified it, you tag it with a DSCP code point, and then throughout the rest of your network, you just trust those code points, so you don't have to, at every hop, re-identify traffic. That would just be a waste of system resources, having to look at each and every packet at every single hop. At every hop, you want to look at this DSCP code point and make a decision on what to do based on what this code point is. So the DiffServ field in IPv4, TOS octet, or the IPv6 traffic class octet, basically it's the 8 bits, and DSCP is bits 2 through 7. 0 and 1 are flow control, so we don't really do anything with those. If you're using IP precedence, I'll just circle this. IP precedence uses those first or leftmost 3 bits, 5, 6, and 7, and DSCP is just the extension of that all the way from the 2 through 7. So DSCP, it's the leftmost 6 bits, and again we do this per hop basis. So once we've identified the packet, say it's a voice real-time protocol packet, we'd typically tag that with a DSCP code point of EF, which is the expedite forwarding. So when we tag it with EF, once it's been tagged, we then operate throughout the network based on that data information that we've put on it, so that DSCP code point. So when we look at the DSCP code point, we've got different levels. We've got the default, which is basically an all zeros, shown here at the top. Let me see if I can get my highlighter. So we've got the all zeros, which is default, with all zeros class selector. So that just means that it's a packet. We haven't identified it. We haven't classified it. It's just the default. EF is expedite forwarding. So EF is our 101 in that leftmost 3 bits. And the expedited forwarding is what we would typically put for traffic that needs real-time protocol. It needs to be always put to the front of the line, a priority queue. Then there's assured forwarding, which is an AF tag, and assured forwarding starts with 001, 010, 011, or 100. And then class selector is IP precedence. And again, class selector would just be those first 3 bits, or excuse me, the last 3 bits. So EF, it ensures a minimum departure rate. Typically we want to guarantee the bandwidth. We prioritize the bandwidth, which means that any packet that we had put into a priority queue always goes ahead of any other packet. If we look at the DSP values, again, 101, 110, It's an IP precedence of 5. Before we had DSCP, so IP precedence of 5, which then corresponds to our assured forwarding capabilities, and then bits 5 to 7 are the same 3 bits that IP precedence uses. Bits 3 to 4 are a drop probability, and bit 2 is just 0. So bits 3 and 4 we'll talk a little more about as well. What does it mean with a drop probability, and just so you understand how the system deals with these packets as they flow through the network. Many organizations don't really utilize the drop probability, but if you're dealing with a service provider that handles your MPLS cloud, they may actually use the drop probability to identify your traffic and to avoid congestion situations on their backbone. So it really just depends on where you're utilizing the solution. So assured forwarding, guaranteed bandwidth, we set up our classes and our configuration to allow a certain amount of bandwidth for those. 4 standard classes, AF1, 2, 3, and 4, and that's where the AAA is binary value of the class, and DD is the drop priority. So when you look at these numbers on the left, and then bits 3 and 4 are the drop probability. So this drop probability, so say I'm in a class of AF1. AF1, if we look at the classes and how they do it for the assured forwarding, the AF goes a prioritization of 1, 2, 3, and 4, where 4 is the most important, 1 is the least important. Then when we get to our drop probability, we actually go the opposite direction. Our drop probability, the less likely to drop a packet has the lower value. So an AF11 has the lowest probability of being dropped, whereas an AF13 has a higher probability of being dropped. So these numbers on the AFs, 1, 2, 3, and 4, go up as far as our prioritization. When we go the opposite direction, or on the last bit, these go, our probability gets higher of being dropped as the number gets bigger. So they kind of work opposite directions of each other. So an AF11 is the least important of the AFs, but it has the lowest probability of being dropped. The AF13 actually is the least important traffic in this situation because AF13 has the least priority of the AFs, but the highest probability of being dropped. So this is just kind of a different way of going about it. It would have been nice to have them line up, but obviously whoever came up with this solution thought that this was a better technique using the drop probability going from lowest to highest. In some situations, many students that I've worked with find it a little confusing. So again, the AF1 is the least important, AF4 is the most important. When we look at the probabilities, the 1 at the second digit there, so AF11 has the lowest probability of being dropped versus an AF13, which has the highest probability of being dropped. So DiffServ node must allocate configurable minimum amount of forwarding resources, buffer space and bandwidth per AF class. Excess resources can be allocated between non-idle classes. So again, if there's situations where a class is not utilizing all the bandwidth that we've set aside for it, that bandwidth does not go unused. It can be used by another class. Reordering of IP packets in the same flow is not allowed if they belong to the same AF class. So it's not going to reorganize. So if you've got an AF1 classification, there's no difference between AF11 and AF13 in a flow. So we can't really reorder that packet. The whole idea of this DSCP code point was backward compatibility with our class selectors. So the IP precedence that we used to use, it's backward compatible. So the class selector really deals with those last 3 bits on the right-hand side, and those bits, if we don't use those, then we basically perfectly align with what we used to do in IP precedence. So again, it just to give us a backward compatibility to RFCs of the past and historical, such that we don't have to redo everything in our network if we were using IP precedents. So before converged networks, so always everybody wants to know, why is this important? You know, when my network's always just functioned fine, I haven't had any issues with my network, why all of a sudden the excitement about QoS? Well, the excitement comes in because of the fact that in the past, when we didn't have converged networks, so our voice and our telephones sat out here on a completely separate network, and the phones never really talked to anything else on our network. Our video conferencing was all done separate on our network. They ran separate from what we dealt with for our data. There was never an issue because the voice was running over the PSTN. The quality of service was guaranteed by the PSTN. There was no concern for us on how packets got through that network. The telephones ran on a complete separate wiring infrastructure within our buildings, typically a Category 3 cabling that was totally separated from any of our regular data networking, our PCs and our servers. Now with the converged network, let me just get to the next slide here. On a converged network, we have everything flowing on the same network. So all of these interesting things out here, like our phones connect to our switches, we now have all of our video connecting to our switches, and we have one network. So this WAN now has to carry all this traffic. And voice and video is very susceptible to delays, to jitter, to bandwidth. You drop packets. You cannot resend a voice packet. Getting my voice, a fraction of my voice 2 seconds later is useless information because it just doesn't fit. So it's really important that those real-time protocols are given a higher priority within our network. Additionally, now with the network's growth and the different applications we're running, we may have special applications out here that are for, say, manufacturing or for HR that are more important than for training or finance or order entry. Maybe our business does have some requirements around order entry because that's how we do our sales. And without our sales happening, we have no business. So there may be applications that are more important, and with this bandwidth being limited, we need to prioritize this traffic. We need to make sure that these applications are given the bandwidth that our business requires of them. So instead of just taking the old way of doing it where we just kind of set up a network and we hope that we've got enough capacity to handle. If we don't have capacity, then users are just waiting. We're actually taking a different view of it now and saying, okay, what are the business drivers? What does our business need to do and need to accomplish? And that's what our QoS is set up to handle, is to really deal with those business needs rather than just saying, oh, well, the network's going to do whatever the network's going to do. That's not the best solution. QoS gives us the ability to really handle those situations. So what are some of the quality issues? Well, if you have your telephone calls going across here, your voice is breaking up, you're going to get maybe some jitter, maybe some packet drops, and so it'll sound like a really bad cell phone call. Teleconferencing situations, the picture could be jerky. The voice may not be synchronized with the video, so people's mouths are moving like the old movies that were out of sync, and the mouth is moving but the sound isn't coming out. You may have situations where the teleconference, the video starts pixelating, and so you end up with these funky black spots in the middle of the picture. Brokerage house, I need that information 2 hours ago, where is it? Your network's bandwidth may be overutilized, or you may not have enough bandwidth, and so information is being dropped or not being handled properly on the network. A call center, please hold while my screen refreshes. We've all had that situation where you call in to your bank or some other entity, and the person on the phone is basically tap dancing, waiting for a screen to come up and give them information so they can help you and assist you with what you're calling about. And that can happen because just network congestion. The bandwidth is all being utilized and they can't get their information. QoS allows us to deal with each and every one of these solutions here and really gives us the capacity to handle what our business drivers and business needs are. But it does require the engineer to take a look at the business operations. someone has to identify what are the key aspects to business. It's really simple when it comes to voice and video. Obviously, it's real-time protocol. We need to set up some prioritization of those conversations and those video capabilities. But when it comes to our other applications, then it becomes business functions. So we really need to look at what does the business operations need from us to make this network proper. So lack of bandwidth. So multiple flows compete for a limited amount of bandwidth. We may have someone trying to download off of an FTP site at the same time that we're trying to do a video conference. Not the best situation. End-to-end delay. So there can be fixed and variable delays. So packets have to traverse the network, device links that add up to the overall delay. So as I get on the network, I'm going to have some delays as my packet hits the network. As it moves from a switch to the router, there's going to be some delays, some time lag as it transmits across those links. There's going to be time taken up with the transmission onto the wide area network. So if my WAN is T1s or a DS3, how long does it take to actually put my packet onto the wire? That's delay. We have processing delay, which could be the router making a routing decision. So the router has to look at the packet and say, where is this going to? And it has to do a lookup in the table to see where to pass that packet to. So that's processing delay. So that's overall delay in the network. We may have access control lists, so we have to look through the access control list. Again, more processing delay. Then we have variations in delay. Variations in delay are called jitter. And what that is say we send a packet from one end to the other of our network and it takes 70 milliseconds. That's perfectly acceptable. 120 milliseconds is also perfectly acceptable, but we now have a change in our delay between 70 and 120. That's a 50 millisecond difference in the amount of time that it takes to get from one end to the other. That's what we call jitter. Jitter is the variation in delay. And if we have too much jitter, then we have buffers on our phone or in our computer if we're using software applications that will play out and now they go empty, which means that that packet shows up late. It's a dead packet. It's out of date. It's not current. So we drop the packet anyway. Packet loss would deal with our packets are being dropped in the network. So within the network, we may have, say, a section that runs through an MPLS cloud that's oversubscribed and the packets are being dropped. We may have a bad interface that's dropping packets randomly. We may have queues that are filling up, and so the router has no choice but to drop packets because the queue is full. So all of these situations will create packet loss. Packet loss causes really big problems to our real-time protocol. So just looking at how does this look again with a visual, lack of bandwidth. So you can see here we've got a 10 meg link, a 256K, a 512K, and 100 meg. So obviously our smallest link is a 256K. That's our bottleneck. So there's a lack of bandwidth. We can get our connections across the network look really good except for the 256 and the 512 on the WAN, and that 256 is really the worst position for us because it's the smallest amount of bandwidth. So our end-to-end delay. So as we move through the network, we'll see that we've got propagation delays. Propagation delay is the actual time it takes to send the electric signals across the wire. And then processing and queuing delay. Processing delay occurs on the device, on the router, as it has to deal with processing that packet. So if the packet comes in, I have to accept the packet. I have to do a lookup in a table to figure out where do I route this to. I may have to look up into the table and into the system and see what queue do I put this in. And then we put it in a queue, and there may be 10 packets ahead of it in that queue. So now it's got queuing delay where it's waiting for other packets ahead of it. And then this propagation delay and processing delay repeats at each step through the network. So those are my delays within the network. Again, to have good quality voice, we typically look at 150 milliseconds one-way delay, or if you wanted to look at it from a round trip, a 300 millisecond round trip, but a 150 one-way delay. And that's what we're looking for real-time protocol. Packet loss. Packet loss, again, is just where a packet gets dropped. Maybe it's in a queue. And this is just showing us a queue where we tail dropped. So the queue filled up. There was no place else to put the packet, so that packet was dropped because the queue was full. That can create issues in our network. Again, if we have areas where we've got small bandwidth and we've got large bandwidth coming into small bandwidth, so we're coming into a bottleneck, we're sending it really fast because we're running at that 10 meg, but that link is only 256K. Well, I'm going to fill up this this queue really quickly if I've got this queue is handling a 256K where I've got a 10 meg in. So that queue will fill up. When it does fill up, then I'm going to have tail drop, and I'm going to lose those packets. So how do we deal with this? Well, the whole goal is to deal with congestion through congestion management mechanisms. And what are those mechanisms? Well, those mechanisms are queuing and prioritization. We want to prioritize our traffic to get different levels of performance and allow us to really get our data that is important to us through the network. So in this situation, we're looking at voice, which is, of course, real-time protocol. That's very important traffic. Then we have mission-critical traffic, and then transactional, which would just be basically everything else. So in order to deal with this, we've got the priority queue, and I'll just highlight that. So the priority queue here up at the top, which is set up for voice. So we create a prioritization queue that will always send the voice traffic ahead of everything else. And then we do 40% of the bandwidth we set up for our mission critical. So we know that this mission critical applications are given a big chunk of the actual bandwidth that's available, and then 20% for everything left, right? So what we're saying is if there is mission critical data, up to 40% of the bandwidth is guaranteed to go to that mission critical. Now the benefits of using the DiffServ model is that if I'm not using that 40% for mission critical, that 40% is available to the transactional. The voice queue, because it's a special priority queue that always goes first, is actually policed to the level that we put it at. Because if we didn't police it, it could potentially overrun every other classification on our network. So the prioritized queue is always policed to the level that we set it at. But all of the other queues can utilize available bandwidth. So if there's bandwidth available, say the mission critical wants 50%, but currently transactional only needs 10%. That would work just fine because the mission critical, anything that doesn't meet the mission critical 40% would then move into the transactional queue and be processed as just a regular packet. So it does allow us to utilize the bandwidth much better and gives us some capabilities that we otherwise don't have on the network. So we'll talk about class-based weighted fair queuing and low-latency queuing in a little more detail so you can understand how these tools work for us on our networks. So class-based weighted fair queuing and low-latency queuing, so that's CBWFQ and LLQ. The idea is the class-based weighted fair queuing is really this portion down at the bottom. So this is just our class-based weighted fair queue. We take our traffic, we separate our traffic into different groups, and then we prioritize or put it out on the network by the bandwidth that we've set aside for it. So this mission critical, we've set up 25% of the bandwidth. Transactional, we set up 10%, and then the class default gets the 25% that's left. Now the priority queue is a special add-on. So really, LLQ is just the addition of a priority queue to class-based weighted fair queuing. So low latency queuing adds a special priority queue, and the priority queue, what it does is if there's ever a packet in this queue, so if this queue ever has a packet, that packet will always go first ahead of any other packet. However, as I mentioned previously, it does put a policer on that queue. So when I put this 40% here for that priority queue, if 41% tries to go through, 1% will be dropped because it will automatically go to 40%. Anything above that will be dropped. So it does police to that level. And again, the reason it polices is if I allowed this to always go first and say 45% came into it, then it would overrun. What if 100% of the bandwidth tried to come into this priority queue? It always goes first. It's always going to go ahead, and we've now basically starved out all other traffic. So if we didn't police the priority queue, you could starve out everything else on the network. So CBWFQ, it's a mechanism used to guarantee bandwidth to specific classes. What are the classes? Well, that's strictly up to you. You as the engineer get to design any classes you want, identify the traffic any way you want, and then decide how much bandwidth you're giving each one of those classes. So it extends the weighted fair queuing. Weighted fair queuing was just to share bandwidth. So it extends this weighted fair queuing and allows you to set up special classes, and you define the match criteria. Any packets that satisfy that are then classed with that class, and then the queue reserves the bandwidth for that class. Now again, that bandwidth, if it's unused, unlike an IntServ reservation, any unused bandwidth is available to the default class. So if you have any unused bandwidth, say you set up 25% for HTTP, and at the time it's only using 20, the other 5% then becomes available to the default queue. So what's the architecture look like? Again, here's just a pictorial of it. We've got the classes coming in. We've got a voice class up at the top. So the voice comes in. Tail drop, again, anything above the queue level is automatically bit bucketed. It's policed to that level. Tail drop from the class 2 will automatically drop down into the class default. So that way it can utilize the excess bandwidth if there is any. So it does give you that capability. But this is just, again, a pictorial of the same information. So what are the benefits? Minimum bandwidth allocation, finer granularity and scalability. So you can be very granular how you call out your classes. You can be very granular in how the packets are classified. So anything you can write into an access control list can be used to classify. So if you want to say this IP address going to this IP address on this specific TCP port or UDP port, that's how specific you can be. So you can really nail it down. You can also call them out by protocol. So there's lots of options for you. MQC interface, easy to use. So again, it's just the ability to type this information in. I'll show you some of the configurations which will help with that. Maximizes the transport of priority traffic. The drawbacks, voice traffic can still suffer unacceptable delay because this is a queuing mechanism. It has nothing to do with delay, cannot change anything about the delay on the network. So delay is not dealt with within class-based weighted fair queuing or low latency queuing. Low latency queuing, priority queue added for CBWFQ real-time traffic typically is what we use. You could actually put anything you want in the priority queue. There is no law that says it has to be real-time protocol. Anything you want can be put in that queue. High priority classes are guaranteed, so low latency propagation of packets, bandwidth. High priority classes are also policed when congestion occurs. Again, as I mentioned before, we have to police that. Otherwise, if we don't, the low latency queue or the priority queue could potentially starve out all other data traffic. They can then not exceed their guaranteed bandwidth. Lower priority classes use CBWFQ. So all we're doing is we're adding a simple priority queue on top of class-based weighted fair queuing. So here's the LLQ architecture. Again, same type of configuration. We've got the policing set up here. So you can see that we police this as we send it through the network. Now, other issues that can happen on our network, one of the big issues that we have is in the old days with things like frame relay where we had slow links less than T1. Today I know that this is really a topic that almost doesn't apply anywhere in the real world. I have talked with a couple of students that recently that work for service providers, and in some of the areas of the world frame relay and slower than T1 links are still used frequently. For most of us in the United States, we're talking T1s or above. Not many companies out there trying to do anything with a partial frame relay link. However, for your CCIE lab, you will be using frame relay. It's on the information sheet for it. It's part of the lab, and that link will definitely be less than a T1. Why? Because it's more difficult to configure. Why would they make anything easy on a CCIE lab, right? So you will have to deal with these potential issues of packetization freeze out, meaning that I've got a really large packet in front of a bunch of small packets. So let's look at this on the screen. We've got this 1,500 bytes of data sitting here, which is a big fat packet. Once it starts to go onto the wire, the router cannot put a voice packet in front of it. It has to allow that packet to go onto the wire completely. So what does this mean? Well, we can create 214 milliseconds of serialization delay to get that 1,500 byte packet onto the wire. That's a huge amount of delay. So that's actually going to kill our voice quality, because obviously 214 is more than 150. It's also going to be a huge jitter on our network, because it's going to cause some packets to be much slower getting into the network than others. So this is going to create some delay and some problem for us. So how do we deal with that? Well, obviously there's ways to deal with it. Again, in the real world, I will just keep pushing. In the real world, this does not come up. Your lab exam, this comes up. So let's look at serialization delay. What are the delays if we have the 1,500 bytes? Again, we could have problems even without going the full 1,500 bytes. You'll see that there's some really large numbers up here. Even with, a 256K, you're getting large amounts of serialization delay. So we don't want to have these big packets in front of our voice packets. We want to break these down to get them small enough that we can slip our packets in. So let's look at some of the process for doing that. What we can do is we can fragment those packets. So instead of having a 1,500 byte packet, we can fragment the packet into smaller pieces, and then we can interleave it. So this is called link fragmentation and interleaving. So we're going to break it up into smaller pieces, and then we're going to allow voice packets to jump in the middle of the overall data. That's the whole game plan here, is just to make it so we're not sending one big chunk. So instead of having that big rig in front of you on the freeway that you can't seem to pass, we're going to break that big rig into smaller trucks that we can then slip in between and get you in and out of the freeway. Not that we all drive the freeway much, but I go frequently Los Angeles and currently teaching in Las Vegas, so the freeway traffic does get pretty bad. Same thing happens with our traffic on the network. So that's link fragmentation and interleaving. Next thing I want to talk about is really getting into sort of the switch aspect of the QoS. I always get people that say, I configured my QoS and my WAN and everything's great there. I don't need to do anything on my switches. I've got 10 gig backbone, or I've got multiple 10 gig uplinks, either channeled together, so I've got a 20 gig backbone. But that's not the case. That truly is not how you should deal with voice on a network. As soon as your packet goes on the network, it needs to have quality of service from end to end. It must be from wherever it enters the network all the way to where it exits the network. You have to set up QoS all the way through. And there's different aspects of QoS that we need to deal with. So with this slide, what we're looking at here is the trust boundary. So at what point do we trust a packet coming into the network? As you can see with option number 1, we have a trust boundary. We trust the endpoint. So at this point, what we're saying is we know it's a Cisco phone sitting out there, and we know that Cisco phones are going to configure their voice traffic and will send us everything properly marked. So the DHCP code points coming from that phone will be correct, meaning if it's skinnier SIP, call control will be set up either as AF31 or CS3, depending on how we've configured it, but it will tag that traffic properly, and all real-time protocol will be tagged EF. So we know that that endpoint is going to do it. So we don't have to go in and configure the switch, the core switches, or the router to re-look at that packet. We don't have to examine the packet. We trust the packet coming from the phone. Now at the next level, option 2, this trust boundary, we don't trust the endpoint. So at the switch level, so the first switch that device hits, that switch is going to have to identify the traffic and then tag it. Now again, the idea is that we classify or tag the traffic as it comes in. We don't have to then reclassify it as it flows through our network. We can just respond to those DSP code points. So in the option 2, we're not going to trust the endpoint. We're going to have the switch actually figure out and retag traffic. The next option is we don't trust all the way up to the core. So until it hits our core, we don't trust the traffic. So we may classify at the edge switch and then reclassify at the core switch. Most organizations don't do this. Most organizations go with this type of a solution here, which is option 2. So where the first switch it hits is the one that is the trusted, and anything outside of that switch is untrusted. So we tag the traffic as it comes into that switch. That's a normal operation. There aren't too many reasons why you would really need to do this option 3. Option 3 would really be overbearing and cumbersome to configure because you should be trusting at your edge. You might have a situation where a different group of people manages that edge switch. Maybe that's not your IT department. Maybe some department has their own switch that for whatever reason they manage themselves, and your department, because you don't manage the switch, you don't want to trust their DSP code points, you don't want to trust their traffic being tagged properly before it enters your network. That would be a situation for number 3. But that doesn't typically happen. That's not a normal operation in most businesses. So the ideal is option 2. Personally, for me, I don't trust endpoints. Even a Cisco phone, I don't trust. There is a possibility something out there is spoofing a Cisco phone. I don't have absolute and total control of that endpoint. So I personally do not recommend option 1, and that's a personal preference. Again, you may feel very comfortable trusting that Cisco phone or third-party phone. I just try to avoid that situation. I would rather tag my packets as they hit that first access switch. That's my personal preference. And really, it's truly a best practice, I think, and I recommend it as a best practice. So access edge trust model, endpoints, so your analog gateways, IP conferencing stations, video conferencing gateways and systems, so on and so forth. Endpoint categories, trusted, untrusted, conditionally trusted endpoints. So from my standpoint, there are some devices that I will trust out there, such as a router. Obviously, if it's a router I'm configuring or a voice gateway that I'm configuring, I'm going to trust it. If it's a server, Cisco Unified Communications Manager server, I'm going to trust that server. That server is under my control, so I'm going to trust the server. When it comes to a client PC, probably not going to trust it. I have no faith that that machine is doing what it's supposed to do, therefore I don't want to trust it. So again, trust boundary extensions and operations. Looking at, you can move the trust boundary out to the phone itself, which then actually requires less work on your behalf because the phone is then trusted. It's a little easier. You don't have to set up access control lists or do any sort of tagging as a packet comes into your switch, but there is the risk that something spoofs that phone, in which case you may have some problems with your trust boundary. So again, this just shows that when the phone sends its signaling or voice packets, the phone is tagging it properly and our switch is trusting that tag. When packets come from the device at the endpoint, the PC could be setting its cost higher, but the phone is going to reset to a cost 0. So anything coming from the device, the end device, meaning a PC or whatever is connected to the phone, would automatically be retagged by the Cisco phone to a cost of 0, DSP code point 0, which is a default, and then forwarded on to the network. So that's just the whole premise of moving that trust boundary out. So let's talk a little bit about configurations of this. When we configure these, you go into the system, you want to do a class map, you can do a match all or a match any, and then you have to give it some sort of a name. So you've got to go in and configure how it's going to work. If you don't put anything, then it's going to do the class map match all. Then when you go into a conditional map, you have to set up conditions. Match an access control list or match a protocol, whatever the case may be. You can also add descriptions to it just to help identify what that class map is. You can also use the not condition. And I think I'm just going to move through these quickly because I'm running on some time here, and I want to get into that demo. So I'll move through this pretty quickly, but the idea is that we can use hierarchical policy maps. So once we have a class map which just identifies the traffic, then we use policy maps to transact or react to that traffic that's been classified. How do we deal with that traffic and give it bandwidth? What bandwidth do we set aside for it? So here's an example where we've got a class map, all traffic match any, policy map, which has a shape to 2 meg, and then the service policy where we've actually put the QoS into that. So here you can see that basically we've got this QoS on this right-hand side, so policy map QoS. It's going to use the HTTP traffic, meaning protocol HTTP, and it's going to allow it 1 meg. Over here, we've set up a shape, and we're shaping everything to 2 meg, and then within it, we're doing a QoS. So all traffic will be shaped to 2 meg, and we will allow HTTP to get 1 meg of the 2 meg. So there you go. So how do we attach the policies? Well, we just go to the interface, and we put a service policy output or input, and we can configure whatever policy we want on that interface. So let's talk a little bit about the 3750 QoS and how that works. So on the 3750, to turn on QoS, it's a real simple option. It's just MLS QoS on the config mode. We've now turned on QoS. Then we can go in and on an interface, we can do MLS QoS trust DSCP. So if you want to actually trust whatever comes from the end device, you can. It's up to you. Again, I don't recommend, but you can do it. And here's an example of setting up a 3750 using IP phone PC Scavenger model. And this configuration information comes right out of Cisco's Enterprise QoS SRND, or Solutions Reference Network Design Guide, which I'll show you in just a moment. So this is really, looks like there's a lot of configuration going on here, and there is a lot going on, but it's not difficult to do because it's all in the QoS SRND. Even on your CCIE lab exam, if you know where to find the QoS SRND, you don't need to memorize all these commands. You can just go copy paste. Some people like to use auto QoS and then make changes to it. I find that auto QoS takes longer to rip back out than it does to go find the QoS SRND and copy the information you need. So here's that documentation, and I'm going to bring up on screen the actual document. So this is the URL. Again, the URL is at the top of the screen. And this is the document here. And within the document, what you'll find is that there's a lot of information that really allows you to do what you need to do. And it appears that it's still downloading. Anyway, so within this document, you can search it and find what you're trying to get to. It holds information about frame relay. It gives all the information about configuring a Cisco 3750 switch. So each of the switches will have information about how to set up the QoS on those switches. Really a great document and resolves a lot of issues. Let me put that URL back on screen here. So if you just go and you do a search for the Enterprise QoS Solutions Reference Network Design, or Enterprise QoS SRND, you will come up with this URL, and that will be the document you need. So now that we've talked a lot about the QoS, and what I want to do next is really just go through a quick demonstration. I'm going to go through it utilizing basically a CCIE lab type of question. This is the type of thing that they're going to ask on a lab. We see these in all of our practice labs. This actually comes from one of the practice labs. You've got a frame relay PVC between HQ and BR1. It's 512K. We want to allow 4 voice calls between HQ and BR1. We want the voice control traffic to get up to 8 kilobits per second of bandwidth. Voice control traffic should use CS3 markings only, so class selector 3. You should use low latency queuing to ensure that voice bearer traffic is placed in the priority queue. All other traffic should be treated as weighted fair queue. And do not enable compressed RTP, so we don't want to do compressed RTP. So I'm now bringing up on screen here. This is a text document that actually goes through and sets this up. So on the router, what we've described so far is we want to class map match all voice. So we're setting up a class map for voice, and we're going to match the DSCP code point of EF. So we're going to assume that this was already tagged as it came into our network. I'm not on the router going to set up how to identify this class of traffic. On the router itself, we're making the assumption that all traffic is properly tagged before it got to the router, which is the way it should be. The router should not be identifying traffic. It should be acting on that traffic, which is what we're doing here. So we're matching the IP DSP EF for voice. And then we have the signaling. So we're going to match any on signaling, and we're going to match the IP DSCP CS3 or class selector 3. So the CS3 is the one that they said, and only CS3. So that's what we've done. Then we're going to create a policy map. So the next piece of this is creating a policy map, and the policy map uses these classes. So you have to configure a class map first. You can't do a policy map before a class map because you have to create the class to then operate on. So I'm now creating a policy map called HQ-BR1, so it's going to go between HQ and BR1. I'm going to identify voice class, and I'm going to give it a priority of 112. So what I'm saying with this, the key command there is priority. When I say priority, I just created a priority queue. So the voice queue just became the priority queue. It has nothing to do with the traffic being tagged EF or anything like that. I can put a priority queue on anything I want. In this situation, I'm using the class voice, and I'm putting a priority queue. The 112. In the statement, it said that we wanted to have 4 phone calls. Now on a WAN, our typical phone call would be G729. A G729 call uses approximately 28 kilobits of bandwidth. So if we multiply our 28 by 4, we get 112. On the real exam, my understanding, and I can't say this is absolutely true because I am not a proctor, but my understanding of the proctors are they don't grade you to an actual absolute bit count. If you had a priority anywhere from 112 to probably 120, no one will get excited. You're going to get the points for that aspect. In the real world, I've looked at Cisco's website myself, and I've found in 3 or 4 different places different bandwidth accounting for it, even when we get into taking all of the overhead into account. It's somewhere between 28 and 30 kbps for a frame relay link. Where exactly is it? Well, that's hard to say. For this example, we're using 28. For the signaling, the class signaling, which used our class selector of 3, we were told to set up 8K. So we have a bandwidth of 8. Notice the difference here. I have bandwidth called out instead of priority. Priority sets up a low latency queue or a priority queue. If I say bandwidth, I'm just setting up the bandwidth. Then the rest of our traffic was set up as fair queue. Now, the problem is that we're dealing with a frame relay link, and we need to do some frame relay traffic shaping on this. It's a 512K link, so we don't want to just send all of our traffic across. We want to shape our traffic. So if we follow that QoS SRND that I had on screen earlier, the QoS SRND says for a 512K link, we should do a shaping. So I'm going to go into a policy map. So I'm going to create another policy. This one I'm going to call it FRTS-512 for frame relay traffic shaping 512K. I'm going to use a class default. The class default means basically I haven't defined any classes, so everything falls under class default. And on this, I'm going to shape. And I'm going to shape the average to 486,400. This number here is in the QoS SRND, and you can go find it in the QoS SRND, or you can know that the calculation is basically 95% of whatever the link speed is. So the link speed is 512K. So if you multiply 512 by 0.95, you come up with 486,400. The number next to that tells me how many bits I want to go per time slice. The simple calculation here is divide the previous number by 100. So 486,400 divide by 100 gives us 4864. And then this last one would be my excess burst. So that was my burst commit. This is my excess burst, which is 0. So shape average 486, 400, 4864, and 0. Then because we want to still perform our queuing within this frame relay traffic shaping, we put our service policy underneath. So this is where we're doing that hierarchical policy within a policy. So we now have a policy on it. But the other problem we have is, we mentioned earlier about starving out traffic. Well, anything that's less than 768K, and again, this comes from the Enterprise QoS SRND, anything less than 768K for a link speed needs to be fragmented. We're at 512K. So we need to fragment. What size do we need to fragment? Well, you can either memorize this number as 640, or you can simply look in the QoS SRND. It has these numbers for you. So you can also do an equation and calculate it, whatever makes you happy. Bottom line is you need to know where to find these numbers, or you have to memorize them. So map class frame relay. So the FR map class 512 is any name you want. This name here can be anything you want. It's up to you. Whatever you want to call this is up to you. Then we want to do the frame relay fair queuing. And then we're going to apply the service policy. Which service policy are we going to use? The frame relay traffic shaping, because we're not only going to fragment, we're going to traffic shape. So we called out FRTS-512. Inside of FRTS-512 is also the policy HQBR1, which actually has how we are setting up our queues. I know it sounds like a lot, but really, if you look, it's not that many steps. It's pretty simple to get through. Moving on down, we have to apply this. So we have to go into the interface. So this is my serial interface that goes from HQ to BR1. Within that interface, I go into the DELC. Here's my DELC. And I apply this frame relay class. So I've done a map class for frame relay. I'm now applying that class to that interface. So if I go back to my device, and I'm currently on the switch, so let me just go get out of the switch. Let me get onto my router. And I can actually copy and paste all of these configs, but I've done that already, so I'm just going to do a show run. Pipe again, interface S0/2/, oops. Well, let's just do a show run. So here I've got my classes called out. Again, the same classes I just had on screen. Now under the serial 201, you'll see that I've got this interface DELC, and there's my class map. And the map class shows right here. So now what I'm going to do is I'm going to do a show policy map interface. And this will show me all the policy maps I have applied. So I have on serial 020.1, DELC 201, service policy, FRTS 512, the class default, which basically says match anything and everything. And this is where I'm actually doing my traffic shaping, right? So on here I'm shaping to an average, and it shows me how that's been set up with my BC of 4864 and my BE of 0. So my target shape rate. And then it tells me I have a service policy applied inside of that other policy. So this is my policy within a policy, or my hierarchical. And on this one, you'll see here that I have my queue stats. So I have my voice class, which says match all. What am I matching? Well, I match on my IP DSP-EF 46. I have my priority set for 112K. I have a class map called signaling, which says match any. And then I'm matching DSCP code point CS3. And what am I doing with that? I'm setting up a bandwidth of 8K. Then under my class default, which is at the very bottom, this is my queuing, and I have a fair queue, which is a per flow queue. So there you have it. That's all the configuration required to do that. So let's look at what we need to do for our switch. So let's look at that. For the switch, we're trying to configure all switches to map cost to DSCP per the QoS SRND. Again, you'd have to know what the SRND looks like, or you'd have to go look it up. Configure the HQ switch ports to allow 4 G711 calls. A G711 call is going to run you around 90 to 93K on ETH. So approximately 93K, but a lot of people just like to round that and call it 100K, but it's up to you. Excess calls should be dropped. Allow 8K of voice signaling traffic. Excess traffic should be marked as class selector 1 or CS1. Allow 2 megs of data traffic per port. Excess data should be also marked down to CS1. So these are our configurations that are required. So this would be, your CCIE lab question type of thing. Not that you would ever want to configure a real world for this. This is not a real world scenario. This is definitely a lab scenario. So let's look at what that would look like in my text file. So the first thing we need to do is we need to set up that map. So here's my QoS mapping. So I'm going to do my DSCP code points. So it's 0, 8, 16, 24, 32, 46, 48, and 56. That corresponds to a CoS of 0, 1, 2, 3, 4, 5, 6, and 7. Then I said that on some of these things, so let me just move this to the side. Let's see if I can get this to a side where I can see both. There's a little bit on the difficult option here. I'm going to try to get both of these on screen so we can have them side by side. There we go. So it said that I needed to have all excess traffic should be marked to CS1. So what that's saying is map policed DSCP 0, 24 to 8. So if it comes in with these options, so my excess traffic that would be voice signaling would normally be marked as a DSCP code point of 24. If it is marked as 24, if it's policed, it's going to change that 24 to an 8, which is 8 is the CS1. So class selector 1 is the same as a DSCP code point of 8. It also says allow 2 megs of data traffic per port, and any excess data should be tagged as CS1. So that's my 0. So if I have a DSCP code point of 0 and it gets policed, I'm going to remark that to an 8. So these two lines here are associated with those excess traffics as well as the cost to DSCP mappings. Now in order to do anything, I have to turn it on, so I do MLS QoS. That actually starts the QoS operations. The next thing I need to do is I need to set up my traffic. So how am I going to identify my phone calls? Well, I'm going to do that through the call control of SCCP. So I'm going to do a class map, match all, and I'm going to name it SCCP. Again, this name here is anything I want. That's my naming convention. I'm going to match this off of an access group. What's the access? Well, I'm going to use the name SCCP. So I define my own. So when we look down here under my access control list, I've got an access control list that basically matches Skinny as well as SIP. Then I've got an RTP, match all RTP, and RTP traffic. So that's RTP. We're calling it out as UDP in the range of 16384 to 32767. Is that perfect? Not exactly perfect, but it will get RTP traffic. Then I'm going to set my policy map for voice ports. And again, the name can be anything I want. This voice port can be any name that I choose. So under my class RTP, I'm going to police 512, 8000, exceed action I'm going to drop. Because they told me to do allow 4 phone calls, any excess call should be dropped. So exceed action is going to be to drop it. So on a G711 call, they're calling that out as 128K. So 4 times 128 would give me the 512. So the class SCCP, we're going to set IP DSP to CS3. So we're actually going to do an action on here where we set the DSP code point. We're also going to police it to 8K. Any exceed actions, we're going to do the police DSCP transmit. What does that mean? That means to use this map above that says police DSCP. So it's going to change it. If it goes above 8K, it's going to change it from a 24 to an 8 and pass it on. And then under class default, we're going to forcibly set everything to a DSP code point of 0 or DSP of default. We're going to police this to 2 meg with 8K bursts. Exceed action is going to be policed, and again, that would put the 0 to a CS1 of 8. Then all we do is we have to apply this on the interface. So on the interfaces that our phones are connected to, This is a phone interface. We're going to put the service policy on that. Real simple. Again, I'll just go out to my switch. I'm going to do a show MLS QoS. You now see that QoS is enabled. And I'm going to do a show MLS QoS interface. And I'm actually going to call out fast1/0/6 so we can just look at that interface. So it's not trusted. It shows that it does have QoS mode being port-based. I'm going to do a show policy, map, interface, and there we can see on port 106 we have a service policy for RTP. Access group is RTP. And then we've got an SCCP, which has an access of SCCP, and it just shows us the basics of what's going on with that. So that's the demonstration of basically doing a QoS configuration for a converged network. And again, the demonstration was really centered around a Cisco CCIE lab exam. If you were interested in really doing a lot with the QoS in the real world, I highly recommend, and for anybody studying for the CCIE, I highly recommend reading that QoS SRND. I've read the QoS SRND. It is a good read. It has great information in it. There's areas that you can skip over. Obviously, if you aren't using frame relay or ATM in your network, you don't need to read those. For the CCIE lab exam, definitely read the frame relay. Definitely read the 3750 area because those are very important to your CCIE. But in the real world, it gives you some great examples that you can really learn from, as well as use that on the real exam. You don't have to go and figure all this out or memorize all these pieces. You can easily go into the QoS SRND and in a couple of minutes find exactly what you're looking for. So if you are interested in getting some training from CCBOOTCAMP, I'll just highlight a couple things. For our voice, we do have 3 classes that we do. The lab mentoring. It looks like I've got lab mentoring on here twice. We actually have the Voice Lab Boot Camp. We have the Voice Advanced Lab Mentoring, and we also have the Voice Lab Foundation class. And the Foundation class is the base level, also known as CIE V2 or V1, which is a Cisco authorized class. If you're interested, again, you can contact Jerry at our office. There's his email address. You can give him an email and communicate with him. We thank you for joining us for this webinar, and hope you found it useful and provided good information. If you have any questions, please let us know. Otherwise, have a great day. Thank you.